Hello, my name is Richard Essex. I'm a researcher at the National Institute of Standards and Technology in the United States. For the short presentation today, I'm going to discuss the use of mass spectrometry as an important tool for determining half-lives of radionuclides. For the purposes of this presentation, when I say mass spectrometry, I generally mean isotope ratio mass spectrometry. For most cases, these would be measurement results from multi-collector thermal ionization mass spectrometers or inductively coupled plasma mass spectrometers. The very high mass resolution of accelerator mass spectrometry can be useful in some half-life related measurements. For instance, if it's necessary to measure isotopic ratios significantly greater than 1 × 10⁻⁶, or if there's an isobaric interference that cannot be otherwise eliminated or minimized. Other mass spec measurement methods, such as gas source mass spectrometry, are obviously necessary for gaseous elements such as krypton or xenon. Although secondary ion mass spectrometry is also a powerful tool for isotopic ratio measurements, its capability to measure isotopic ratios from specific locations of a solid sample isn't typically needed for the type of measurements used for determining half-lives, and better measurement precision can be achieved using multi-collector instruments. Elemental concentrations are also measured by mass spectrometry. Typically, sector field or quadrupole ICP-MS instruments are used for these types of measurements. The way these instruments might be used for half-life related measurements is for the identification and quantification of contaminating or interfering radionuclides in activity measurements of a target nuclide. There are a variety of ways to measure half-lives. Of course, the classical method is to measure the change in activity of a quantity of target nuclide over time. Then, fit an exponential curve to the resulting data to determine a decay constant for that nuclide. For nuclides with half-lives of decades or more, it is often impractical to determine half-life by measuring the change in the activity of a sample over time. Instead, for these longer-lived nuclides, half-life can be determined by accurate and precise activity concentration and amount concentration measurements on the same material. Another way of determining half-life is by measuring the ratio of a parent nuclide to a progeny nuclide. For this method, mass spectrometry is used to measure an atom ratio of a longer-lived parent to a shorter-lived progeny nuclide in its decay chain. This method does not require that you know the amount of material, nor does it require an activity measurement. However, the parent and progeny nuclides must be in secular equilibrium, and the half-life of either the parent or the progeny must be known to determine the half-life for the other nuclide. A third method for determining half-life using mass spectrometry incorporates components of the previously described methods. For this method, the isotopic ratio and the activity ratio is measured for a pair of nuclides. It is not necessary for these nuclides to be in secular equilibrium. In fact, they don't need to be part of the same decay chain. It is, however, necessary to know the half-life of one of the two nuclides, and both the activity ratio and the atom ratio need to be precisely and accurately measured. Now I'd like to go through several published examples where mass spectrometry was used for half-life measurements. For this example, NIST, in collaboration with US DOE labs and CEA in France, made a half-life measurement for thorium-229. The graph in the upper left shows the variety of methods used to measure the activity concentration of a thorium-229 solution. The graph in the lower right shows the amount concentration measurement data for the same solution as measured by isotope dilution mass spectrometry. With these two measurement values, the decay constant calculation is straightforward. The blue circles in the amount concentration graph are individual IDMS measurements. This data shows how robust this method can be. The measurements for this study were made by 3 labs using 3 different thorium spike preparations over 2 measurement campaigns. Despite these variables, the resulting repeatability of this data was 0.08% relative standard deviation. In this example, Cheng and others determined half-lives of uranium-234 and thorium-230 nuclides by using the U-238 half-life and measuring the atom ratio of these decay progeny to U-238 on multi-collector mass spectrometers. These measurements were made on geological samples where the decay chain was assumed to be in secular equilibrium. This graph shows their results for the thorium-230 U-238 ratio measurements on a Table Mountain latite rock standard and on zircon, Iceland spar calcite, and uraninite mineral samples. In another example, Maruli et al. Recently measured the half-life of americium-243 in an americium CRM by comparing the activity ratios of americium-241 and americium-243 as measured by alpha spectrometry to the well-characterized isotopic ratios measured for these nuclides in this material. Of course, the activity ratio is directly related to the decay constants and the amount of each nuclide in the material. So using the well-defined decay constant for americium-241 and the measured activity ratio and atom proportions of the isotopes, a decay constant for americium-243 was calculated. There are also indirect ways that mass spectrometry can contribute to the determination of radionuclide half-lives. As previously mentioned, in some cases, mass spectrometry for element amount measurements may be used to improve activity measurements by allowing for higher precision corrections for contaminating radionuclides in activity measurements of a nuclide of interest. High-precision isotopic ratio measurements can also improve activity measurements by quantifying isotopic impurities that are impossible to separate from an element of interest. For example, Kikunaga and others used the activity ratio of uranium-232 and uranium-233 in a study to measure the half-life of the U-233 daughter product, thorium-229. They used uranium isotope ratio measurements to correct the 233-232 activity ratio for interferences from other U-nuclides. In a final example, here's a case where mass spectrometric measurement data were not available but could have resulted in substantial improvements for an activity measurement. When Fitzgerald and others determined the activity concentration for the thorium-229 SRM 4328C, the correction for the thorium-228 activity in the solution was the largest single contributor to measurement uncertainty. For this study, a thorium-228-229 activity ratio of 0.017 was measured. This corresponds to an atom ratio of 4.1 part per million. Given this ratio and the type of material, it would not be routine, but measuring this ratio with an expanded uncertainty of 1 to 2% is quite possible with modern mass spectrometers. With this level of uncertainty applied to the thorium-228 correction, the relative expanded uncertainty for the SRM activity values could have been reduced from 0.31% to 0.23%. So, in summary, there are a variety of methods for measuring half-life of radionuclides, and mass spectrometry is an important tool for several of these methods. For instance, when amount and activity is used to measure half-life, isotope dilution mass spectrometry is one of the more accurate and precise amount measurement methods, particularly when only small amounts of material are available for analysis. For other methods, mass spectrometry is integral, such as when parent and progeny atom ratios are being compared, and, of course, when activity and isotopic ratios are being compared to determine half-lives. Finally, this slide lists the references for various studies cited in this talk. I've also included some example references to other half-life studies that incorporate mass spectrometry. I recommend the PAME 2015 paper referenced here. This paper provides a detailed discussion of uncertainties associated with half-life measurements, including some of the measurement methods described in this talk. Thank you for your attention and your interest in this topic.